Now let us examine this particular function using both the first and the second derivative. The first derivative is going to be the derivative of e, which is just e, so it's e to the negative 3 divided by x, but we have to multiply by the derivative of the inside function. Now, just to make it a little bit easier for you, we have e to the negative 3 x to the negative 1, if you want to write it like that. The derivative of the inside function, we would bring down that negative 3 would come along for the ride. We'd bring down that negative, so that would make that a positive 3, and we'd have x to the negative 2. So our first derivative is going to be e to the negative 3 divided by x, okay, all divided by x squared, and we'll have that 3 up top here. So that would be our first derivative. Just a few quick notations here for our first derivative and also for the function itself. Y of 0 does not exist. It's going to be a point where we have a 0 denominator. And y prime of 0 also does not exist. It's not technically a critical number. It's going to be more than likely a vertical asymptote for this particular function, since we have an undefined original function. The question then is, when is the first derivative equal to 0? Well, if we look at the first derivative and we simplify this even one more step, with a negative exponent there, what we have here is 3 divided by x squared e to the 3 divided by x. And the question then would be, when is this equal to 0? We know that there really is no points where it does not exist. We do have a vertical asymptote, but is this ever equal to 0? Well, we know that a function is equal to 0, a rational function, when its numerator is equal to 0. And there are no points of x for which this is going to be equal to 0, so we can conclude that there are none. If we do make a little sign chart for this, it's going to be a pretty easy sign chart, because there are no points where it is equal to 0 or it is undefined. And if we plug in any value of x, this is always going to be positive, and e to the 3 divided by x is also going to be positive. We know at 0 it's undefined, but so is the original function, and it's going to be positive everywhere. So the original function is going to increase on the entire domain, and we're going to have no extrema. But let's also take a look at the second derivative here. I'm going to rewrite this first derivative so it looks like this, to make it a little easier for us to find the second derivative. So what we're going to do here is use the product rule. So y double prime, we have the first times the derivative of the second. Now the derivative of this second is actually this. So I'm going to rewrite this as 3x to the negative 2 e to the negative 3 divided by x. This is the derivative of e to the negative 3 divided by x, because that's what the original function was. So that's the derivative. So the first times the derivative of the second plus the second times the derivative of the first. Well, the derivative of the first is going to be a negative 6x to the negative 3. We bring down that negative 2, making that a negative 6, and then subtract 1 from the exponent. So what I can do here is factor out an e to the negative 3x, 3 divided by x, so y double prime, and multiply this out. I'm going to get 9x to the negative 4, because I add exponents, minus 6x to the negative 3, all times e to the negative 3 divided by x. Let's simplify this one more step. We'll get 9 divided by x to the 4th minus 6 divided by x cubed. And this is actually 1 over e to the 3 divided by x. A common denominator is going to be x to the 4th. So what I get here is 9, oops, let me rewrite this. I'll just rewrite this below. It's going to be 9 minus 6x divided by x to the 4th times e to the 3 divided by x. Getting that common denominator. It's going to be, again, undefined at 0, but the interesting thing is y double prime is equal to 0 when that numerator is equal to 0. So 9 minus 6x equal to 0. We can solve that, and what we get is 9 divided by 6 is equal to x, which dividing by 3 is going to be 3 halves. So if we make a little sign chart here for the second derivative, at 3 halves we get 0, and we just need to find some values to the left and to the right. I'm going to pick 0. If I plug 0 in, well, of course I can't pick 0 because of course that's where it's undefined. I always like to pick 0. Let's pick 1. If I put 1 in, my denominator is going to be positive, and in fact my denominator is always going to be positive. So my numerator is going to be 9 minus 6, which is positive. If I put a negative 1 in, denominator again is always positive. The numerator is going to be positive. And then let's pick in 2 here. If I put 2 in, the denominator is always positive, but the numerator is going to be negative. And so this particular function, y, is concave up on negative infinity to 0, union 0 to 3 halves, and y is concave down on 3 halves to a positive infinity. We have an inflection point at 3 halves, and this is an examination of this particular function.